let's jump right into part 1 of 2 for the organic chemistry pre-finals review. We'll start with some warm-up questions on hybridization. Let's look at the central atom for each of these molecules and figure out what is the hybridization and the bond angle for what we're looking at. So the bond angle will typically go around that central atom. So for example, with water, there is the long way and short way to do this. Why is your toddler me? Well, if you have buggies, I hope you can wipe it on your own tissue. But yeah, you know, sometimes we just got to be like a toddler. All right, so we see a problem like this. It should be a pretty simple, pretty straightforward question. So the long and short way to do hybridization is we can count out all the groups and we can draw it out and we can think about all the, I don't even remember the long way to do this because honestly, that is too complicated. When it comes to hybridization, what I like to do is look at that central atom and count the groups around it, remembering that a group can be an atom that is bound more than once, meaning single, double, or triple, or a lone pair of electrons. So for example, with water, we have one lone pair and a second lone pair. And that means I have a total of 1, 2, 3, 4 groups around it. So what I'm going to do to find hybridization is just count 1, 2, 3, 4. 4 fingers. S, P1, P2, P3, SP3. It's that simple. And I'm going to show you a quick table, but this should be something that you don't even have to take the time to memorize. It should be that straightforward. When I'm looking at the number of groups around an atom, I can have 4, 3, or 2. In general chemistry, you would have learned even more, but in organic chemistry, we're typically looking at 2, 3, and 4. And what you're going to do is count. You know, the counting you used to do on your fingers when you were little, that is what I want you to do here. 4, you count 1, 2, 3, 4. What does that come to? S, P1, P2, P3. That is SP3. If you're counting 3, 1, 2, 3, what does that come to on your fingers? S, P1, P2. That's SP2. And if you're counting on your fingers and you only get 1, 2, that comes to S and P. That is SP. So let's start by counting all the groups. And we already did the oxygen. We counted 4. That's S, P1, P2, P3, SP3. Let's look at the carbon in this. I meant to do acetonitrile, so I'm missing right here. I tried to do molecules that you're going to come across in your reaction. So for example, acetonitrile, this is a common polar aprotic solvent that you have to know. And the carbon in acetonitrile has 4 bonds. 1, 2, 3, 4, but that is not what we're counting. We are counting the total number of groups around this carbon, and that is 1 and 2. Count on your fingers, 1, 2, SP. That makes the carbon SP hybridized. Let's take a look at this carbon over here. Seeing that it has a double bond to the oxygen, 2 single bonds to carbon, there are no lone pairs, no invisible groups to count. What do I see? 1, 2, 3. SP1, P2, SP2. Are you starting to see where I'm going with this? At how quickly and easily you can just run through it, and there you go. There's the answer. Let's look at the next one. For boron, I see 1, 2, 3. SP1, P2. That's SP2. A quick favor, I'm noticing some questions like this. Does she post the video after the live? For the students who have been here for a while, if you can just keep an eye on the chat and help the newer students, I would really, really appreciate it, because I'm seeing a lot more comments coming in than I'm used to. And this way, if I don't have to sidetrack for those, I can focus on teaching and answering your questions. And if you can take care, and I already see quite a few of you did, so thank you. Thank you so much. I wrote more practice problems for today than we will have time to get through. And so I would love to get through as many as possible. And I'm sure you would as well, within reason, right? We're not going to stay here all night. So let's continue. The next one is a carbocation. This is a tert-butyl carbocation that you will see in your reactions. And what's unique here is that we have a charge, but that charge should not throw you off because we are looking for groups that are atoms or lone pairs. And so in a situation like this, let me know in the comments what you think the hybridization is as I count 1, 2, 3. 1, 2, 3. sp1, p2. And that is sp2, even though I have a positive charge there. That doesn't change it. Carbon dioxide, and we'll look at the carbon atom. Even though it has 2 double bonds, and typically you see a double bond and you think sp2 hybridized, for example, as we have over here. Oh, this is so messy. Hopefully you can still see the molecule, the drawing underneath. When we see a triple bond, we're thinking sp hybridized, but in this case, even though it's double and not triple, the fact is I have 2 groups around it. 1, 2, sp. So this central carbon is sp rather than sp2 hybridized. And if you look at the oxygen atoms, you'll notice that each one has a lone pair of electrons. That means I have 1, 2, and 3. So the oxygen atoms are not 3, sp1, p2. These are sp2 hybridized because they have 3 groups around them, but that central one, let's just do it like that, but that central one is sp. If you're with me on hybridization, give me a thumbs up in the comments. Let me know if you have any questions on this. I want to make sure it's clear before we go on to the next topic. Why can we ignore the carbocation? I'm not sure I understand the question of why can we ignore the carbocation. Are you asking why we're not counting the positive charge as one of the groups? If that's the question, the positive charge is not a thing. It's not a pair of electrons. It's not a bond. It's not an atom. A positive charge simply means, I think of it as hungry. When you're hungry, you feel hunger in your stomach. It's not a feeling of something physically present. It's a feeling of a lack of something there. That carbocation, that positive charge is a formal charge of +1, and that comes from not having as many electrons as it wants. So if we look at formal charge, let me know in the comments what equation you learned for calculating formal charge. Question, how do we know to count the lone pairs or not? In H2O, for example, it has 2 lone pairs, and we counted those as something around the central atom. In the second example, you didn't count them on the N. Let me clarify. In the second example, I didn't look at the N. I looked at the C. But if I want to find the hybridization for the nitrogen, I would also count the lone pairs. So if I look at the nitrogen, it has 1, 2 groups around it, sp. So the nitrogen is also sp hybridized, even though carbon has 2 atoms attached to it and nitrogen has 1 atom and a lone pair, they are both sp hybridized. So really good question. Ayala, thank you. I appreciate that. All right, so looking at formal charge, let me think if I remember the equation. Half the number of bonding electrons plus lone pairs plus, I don't know, some crazy, almost looks like a trigonometry algebraic expression. I never liked that. And so I came up with the equation. I went to office hours. My professor belittled me so much that I don't know that I even went back after that. I was just trying to understand. And I said, you know what? Screw this, screw office hours. I'm going to figure it out on my own. And I came up with the equation should minus has. This was, sheesh, almost 20 years ago at this point, and I've started seeing other people teaching it. Should minus has is a much, much easier way to calculate formal charge. So let's use a simple example of the hydronium ion, something you're going to see a lot in reactions. If we're trying to find the formal charge on the oxygen atom, instead of counting bonds and dots and electrons and all that craziness, just look at how many valence electron should the atom have. Oxygen should have 6. How many does it have directly attached, touching that oxygen? 1, 2, 3, 4, 5. Has 5. 6 minus 5 is +1. That is the formal charge of +1. So going back to the example where I give you the carbocation, it's a carbon bound to 3 other carbons. I give you 3 other methyl groups. And in this case, first, for the hybridization, we looked at the carbon and we count 1, 2, 3. 3 groups around it. 1, 2, 3, sp1, p2. That gives me sp2. But then when I do a formal charge calculation, carbon should have 4. Directly attached, I only have 3. That's how I get the positive 1. So that plus is me calculating the fact that it has a formal charge of +1. And what that really means is an empty orbital. It's an empty p orbital available for attack rather than something specific in there. And so that is why it doesn't count towards the hybridization, because it's empty and therefore there are no electrons in there to hybridize. I didn't see who asked that question, but hopefully this helps clarify a little more why the carbocation, why that positive specifically is not counted. So let's move on to another very important topic. We are going to come up with all the resonance contributing structures for a molecule that looks like this. And then we want to find the resonance hybrids. So I'm just making them plus hybrid or I will forget. All right. The thing about resonance is that you want to follow the electrons. And I find it easiest to start with the most negative and move in the direction of the positive. So the most negative would be a negative charge. If I don't have a negative charge, then I look for either a lone pair or a pi bond, and I move in the direction of positive charge. I can start right here with this lone pair of electrons. So let's change the color. And we show an arrow coming from those electrons towards the direction where it's going to move. When this moves down, I'm essentially forming a bond right there, which means even though I can't see all of it, there is a hydrogen here. This carbon already has 4 bonds. It already has a complete octet. And adding that purple bond is going to give it way, way too many electrons, which means as a result of the electrons collapsing down, these electrons will have to get kicked out, and specifically they get kicked over to the other carbon atom. So let me make sure that's very clear. If the pi bond sits between these 2 carbon atoms, if this one gets attacked by resonance, meaning if the resonance go towards that carbon, the only other place to hold that electrons would have to be the other carbon atom, or in this case is carbon, it could be an oxygen or nitrogen that used to hold the pi bond. That would give me the first resonance contributing structure. What I often see, and I want to make sure you don't do that on your exam, is to take these electrons and move them this way. And the reason we cannot move them this way is this carbon right here is sp3 hybridized, which brings me to, if you take away nothing else from today except for this rule, I will be happy enough. Never, ever, ever, ever resonate onto an sp3 carbon or similar atom because they already have a complete octet. And so that's why it has to stop right there. It cannot go further. What does this look like? First, draw a double-headed arrow to show that it's going in between the 2 structures. Redraw the skeleton as you see it, and then pay attention to where the things moved. I have the purple bond sitting right here between the carbon that had the negative charge and then this carbon right here. The green electrons collapse to sit as a lone pair at the top. Now, what happens to the charges? If you think of it logically, then you can see that I started with a negative, and when I get a lone pair, I get a negative. That is one way to get the charges. Or the way that I like to think of it is if this carbon here had a negative charge, negative means too many electrons. A lone pair is 2 electrons. A bond is only 1 electron, so went down from -1 to 0. Well, technically went up from -1 up to 0, and that's why it's neutral. Meanwhile, this carbon here, used to have 1 electron from that pi bond. Now it has 2 electrons from the lone pair. It has 1 extra negative. And so it goes from 0 to -1. That is another way to identify your charges, especially if you don't want to take the time to draw out a formal charge, to calculate a formal charge for them all. I'm seeing some really nice comments coming in, guys. Thank you so much. I love teaching. And when I hear that students are actually taking the time and going through the videos and doing the practice and learning and doing well, this makes it completely worth it, even if it means doing extra sessions before finals, because if you can email me in a couple of weeks and tell me that your final went well because of this session, you will make my day and you will absolutely make my holiday season. All right, so we have our resonance. These are the 2 structures. So we put them into brackets. And then the resonance hybrid is the structure that exists in reality. So this is one extreme, this is the other extreme. But it's not that I have one and the other. In reality, what I have is the electrons going back and forth, with a partial negative on one, a partial negative on the other. And totally forgot what I was going to say after the end. So we have the charge distributed where it's going so fast, it is resonating so fast between the 2 that we have the in-between. And this is called the resonance hybrid because it's a hybrid of the structures that we drew. Let's try one more. And if you have questions on this in the meantime, go ahead and type them in. If you're watching the recordings, I do try to check and answer all the comments. So any questions that you have, just post them in the comments, even after the fact. I don't care how long it is after the fact. I have had this channel for over a decade, and I have been answering comments for over a decade. So chances are I'll get back to you no matter when. Looking at this structure, let's see if we can come up with all the resonance contributing structures. And the question, though, is where do I even start? So let me know in the comments how many structures you think we're going to see. And I'll go back to my rule of start with the most negative. In the last example, I had a negative charge, so that was very easy. In this example, I do have a lone pair of electrons, 2 lone pairs on the oxygen atom, but here is the problem. There is no way to resonate from the oxygen or even from this entire carbonyl to the rest of the molecule, because right here in the middle, I have an sp3 carbon. Resonance cannot jump. If it is not directly attached to something that can resonate, that's it. It is done, meaning I can't bring any of the electrons over. So this is not going to participate in resonance. Instead, I have to start at the most negative electrons that are able to resonate, and that would be these 2 right here. If I have a positive charge, as a reminder, that is an empty orbital. Electrons can resonate into the empty orbital. So let's go ahead and grab a pair that is right next to it. For the sake of, I don't want to draw this a million times. Let me try. Oh, here we go. It's close enough. We'll take these electrons that I marked in purple and resonate them towards the positive charge. Draw the double-headed arrow, redraw your skeleton minus the bond that just moved. Let me put that on. That should help. There we go. So now we have the purple bond sitting right here. The blue bond has not been touched, but what happened to my charges? If this right here was positive because it was missing a bond, missing an electron, and now there's a bond there, that electron filled the void. It filled that open space, and so it no longer has a charge. That means it lost the positive charge. You can take your time to do a formal charge, or you can use the shortcut of it was positive, it gained a bond, it is no longer positive. But this one right here used to have a bond, it used to have an electron, now it has one less. The charge went down from 0 to, when I say up and down, we're referring to electrons, so I'm kind of referring to them backwards, but the number of electrons went down. That means it now has a positive charge right here. Or another trick you can think of is the atom that lost a bond is now positive. It had a bond. It no longer has a bond. Easy peasy, positive charge. Let's see how easy that is by doing the next one. We'll turn these electrons green. We'll move them over, electronegative electrons, into a positive empty orbital. Why am I not giving myself enough space? There we go. We'll copy our skeleton. The purple bond in this case has not moved. The green bond moved down here. It had a positive, it got a bond, it is now neutral. This had a bond, it's now empty, it's now positive. And these are my 3 resonance structures. Question, how do you figure out which is major or minor? That is a very good question. Sometimes you're going to see extreme separation of charge. So for example, if I have something that looks like this with a pi bond, I can technically take this and resonate like so, redraw the skeleton, and now the electrons are sitting here. That's extra, that's negative. This one had a pi bond and lost it, that's positive. These are my 2 contributing structures. I want to go for the most stable, meaning the least amount of charges, and ideally the least separation of charge. And so in this case, why did that count out? Hang on, don't go anywhere. I'm right here. Where did my tablet go? Can you guys still hear me? Something went wrong. Clearly something went wrong. Just bear with me, I'm connecting my tablet again. There we go. That was weird. It just conked out on me. Okay, so you can still see me. The tablet is back on. Give me a thumbs up if the tablet and my little window are both clearly visible to you. All right. So going back to the question of which is major and minor, in this case, because this one is neutral, there's no separation of charge. There's not a lot going on. This is major. This one has complete separation of charge. This is minor. Going back to the previous question, there is no real difference between the 2 because as you see, there's there's symmetry in the molecule. The right and left half look exactly the same. So there's no major minor there. And then over here, it's kind of the same situation. So again, no major minor. But if you have situations where it's a positive on this atom or that atom, 2 charges or no charges, that's when you say, which atom can best hold the charge? Which one has the least amount of charge? That would be the major. So I forgot who asked that question, but hopefully that is clear because that is a very, very good question. And you may be asked for that on your exam. Now, for even more resonance practice, make sure to try the quiz on my website. If you comment resonance, I'll reply with the link. Yes, even if you're watching the recording. So just put resonance in the comments. All right, for the next problem, I was really hoping to have time to draw this before, but toddler boogies took precedence. Okay, so let's do acetyl salicylic acid. Don't worry, you do not have to know the structure. I just Googled drugs and just names that you would recognize, just so we can make it a little bit more exciting. So this molecule right here is acetyl salicylic acid, which is known as aspirin. And what we want to do is identify all of the functional groups in this molecule. So look at it, think about anything that is not just a carbon bound to a carbon and a hydrogen, like a pretty straightforward carbon or hydrogen, and then consider what kind of functional group we're looking at. Okay, so let's see. I see what looks like a benzene ring. Technically, it is a benzene ring, but some professors want you to call it an aromatic ring. So an aromatic ring Or some professors want you to call it an aryl group. That is just another way of saying aromatic ring is an aryl group. What else do I see? Coming off of the ring, I have a C double bound O and then an OH. This is not an alcohol. This is a very common mistake. When I have what looks like an alcohol on the same exact carbon as a carbonyl, meaning that one carbon is holding the carbonyl and the OH, this is a carboxylic acid. I'm just going to put carb acid to make it a faster way to write. And then I have this drunk looking thing over here. So the question is, what do I have? It looks like it's trying to pretend to be a ketone because it's a carbon double bound to an oxygen. But if I have a carbonyl with an oxygen on that same carbon, it kind of looks like it wants to be a carboxylic acid. But instead of having another hydrogen here, it has a whole other group attached to it. This is an ester. An ester is like a carboxylic acid with a chain that keeps going. I saw in the comments aldehyde. An aldehyde is when you have an R group, and then attached to that at the end of the chain, you have a carbonyl with a hydrogen, which is very, very close, but not, we don't have the hydrogen at the end. This thing keeps going. I also saw in the comments a benzoic acid, which is correct. This right here is technically a benzoic acid, and this is not a benzoate because it's the other way. A benzoate, just to clarify, is when I have what looks like a benzoic acid, and that ring is just a shortcut for drawing those 3 pi bonds. It would be this way, then the O, and then the R group. This is a benzoate. But because the oxygen is in between the carbonyl and the benzene ring, that is not a benzoate. So just a fun fact there, the oxygen position matters. Question, are there any variations of carbonyls that create different functional groups? Yes, that is a really, really good question. So you have a carbonyl, and then depending on what you have on the carbonyl, you can have so many things. If I put an R group and another R group, that's a ketone. If I have a carbonyl and I put one R group but I end it, that's an aldehyde. Aldehyde is terminal, ketone is internal. If I have this right here with an OH, we've already seen the carboxylic acid. And if I take that carboxylic acid, but instead of the oxygen, I put other groups here, this would be a derivative of carboxylic acid, which could be, and this is something you learn in Orgo 2, you can have your esters, your amides, your acid halides, and quite a few more. You are very, very welcome. Let's try one more to identify what groups we can find. And this one is going to take a bit. So maybe I should have chosen something shorter. Okay, so as I'm drawing it, I want you to start analyzing and telling me what groups you think you recognize. All right, this molecule right here is THC, tetrahydrocannabinol, which is interesting because it looks very similar to CBD, something I was interested in because a lot of people say take the CBD, not the C. I'm not telling anyone to take anything. I'm just telling you what I heard. So I was curious about the difference in the structure. So what are the functional groups that we see on this molecule? Let's start with, I see a benzene ring looking thing. We will call this either benzene or an aryl group or an aromatic. Actually, benzene is by itself. So in a molecule, it should really be called an aromatic ring. So we'll just do that, aryl or aromatic. What else do you see? Alcohol on the ring, absolutely correct. So this right here is an alcohol. What else we see? There's a pi bond. I'm trying to highlight just the pi bond. Let me just draw it like this. There we go. That's an alkene. What about this oxygen down here? This would include the groups around it. So that is an ether. Not an ester. An ester has a carbonyl. An ether is just an oxygen in between the two carbon atoms. This is what I want to see from everyone. Easy, because as you practice and practice and this gets easy, you'll have a much, much easier time getting through your final exam. Question, isn't that a phenol, not a benzene? If I have a molecule that looks like this, and that color is not really showing up as different, so like that, just a benzene ring with an alcohol on it, that is called a phenol. Absolutely correct. But in this molecule, there's so much more going on. It's not just a phenol because there's a lot more around it, but that is a very, very good question. Now, when it comes to naming these functional groups, let's see how we address them all. But we'll start with a warm-up problem, just something straightforward and simple. I like to start with the parent chain. So let me know what you see as the parent chain, how many carbons in the parent chain, and we'll put the names together. Once we get into the later ones, I also want to include stereochemistry, but this will be a warm-up problem. All right, so typically for the parent chain, it's common to look for the one that looks like it should be the parent, but that's a trick. You want to look for the longest carbon chain. So let me know yes in the comments if the way you figured out the longest carbon chain was going, this doesn't look right. Is it this one? Is it this one? Is it this one? Is it this one? And then finally, after counting a few ways through, you landed on this one. So let me know a yes or no. Is this how you correctly found the parent chain for this molecule? And while you're typing that in, I'll start numbering 1, 2, 3, 4, 5, 6, 7. I'm seeing a lot of yeses come in, and that is correct. But think about it for a moment. You went this way and that 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 way. Under pressure of an exam, that is too much. So how about a faster way? I borrowed this from physics. We're going to call it the junction rule. We're going to find an area that is a junction on the molecule. We'll start here and just find the longest chain coming out of it. So I have an option. So this is the parent goes this way regardless. But the question is, do I go this way or this way? Going down is longer, so I know that this is part of my parent. I find another junction here. I know that this is part of the parent, but do I go this way or this way? Going up is longer. And so without having to count up and down, right and left, over and over and over, I just find a junction, find the longest piece. Find the junction, find the longest piece. And then you'll notice I didn't confuse myself at all, and I just very quickly identified my longest carbon chain as 7. This is kind of what we're doing. We're cutting one piece, we're finding the longest chain. We're cutting a piece, finding the longest chain. Exactly. Okay, so now that we have our 7, let's break it up into the puzzle piece approach rather than just coming up with a whole name. I like to start with a first name. That is hept, because I have 7. Only single bonds gives me ane. My substituents are a methyl on carbons 3 and 4. So I have to put both numbers, a comma between numbers, dash if I have a number going to a letter. And then I have to put dimethyl to show that I have 2 methyls. So di tells me 2. The numbers tell me where they are. And that's it for this molecule. So we put the whole name together as 3, 4, dimethyl, and then heptane. So far, so good. Let's try something a little bit, tiny bit more difficult. Let me know in the comments if you consider this easy, medium, or hard. And let's see if you can come up with either the name or somewhere close to the name. Question. After finding the parent chain, how do you know which way to number it? Very, very good question. If I don't have any high priority functional groups, then I go for the total lowest set of numbers. Numbering it this way, my substituents came out to 3 and 4. But had I numbered it from the other direction, 1, 2, 3, 4, 5, 6, and 7, the substituents would have been 4 and 5. So it's 3 and 4 versus 4 and 5. 4 and 5 is a higher total set of numbers. 3 and 4 is a lower total set of numbers. And so I go with the 3 and 4 so that I have the lowest total set of numbers. I hope that's clear because that's a very good question. But then we have something like this, where it doesn't matter what the total set of numbers is. Because if you have a carboxylic acid derivative, meaning something that would have been a carboxylic acid if it had an OH, but it has other higher priority groups on it, this is going to be an automatic number 1. And so I have to start counting from the amide. Instead of trying to name the whole thing and getting overwhelmed, let's go one step at a time. I have 5 carbons in my parent chain. That is a first name of pent. Only single bonds gives me a last name of ane. I have what looks like 2 functional groups, an amide and an alcohol. When it comes to functional groups, if I have more than one, then the higher priority functional group is the functional group. The lower priority gets demoted from being a functional group to being a substituent. And that means the alcohol becomes a substituent and the amide remains the functional group. So I have a last name of amide. And I don't need to put a 1 because the amide is automatically going to be at carbon number 1. And that means it's self-understood. I don't have to put that here. All right, so what do we have for substituents? I have a methyl sitting on the nitrogen for the amide. So instead of a number, I put N-methyl to show that it's on the amide. And then the alcohol is 4-hydroxy. When alcohol is not the highest priority, we use hydroxy rather than the OL ending because it became a substituent rather than a functional group. Given that the alcohol is on a wedge, I also have to include stereochemistry. Let's not forget that there is a hydrogen in the back. And so we're going to number the substituents using the Kohn-Ingold-Prelog system. How do you know? How do you include RNS? We're going to put it at the start of the name. So in this case, we have the oxygen on alcohols priority number 1. Hydrogen is always number 4. Methyl in the presence of hydrogen is always number 3. And then the rest of this chain is going to be number 2. Notice I didn't have to do any kind of evaluations because of the trick that I teach you for stereo. Hydrogen and methyl automatically got ranked. And so number 2 was my only other available number to use. That made it very easy. Cross out number 4, trace an arc from 1 to 2 to 3, and I get R for the oxygen. So I'll put an R over here. And because there's only one stereo center, I don't have to put a number. If I had a chiral center on 2 and a chiral center on 4, then I would have to say 2S, 4R. But in this case, I just put the R. And I believe that is everything. So let's put this entire mess together. We start with the R because the stereochemistry comes before the name. Then we put our substituents in alphabetical order. So I have 2. I have M and H. H comes before M. So that will be 4-hydroxy. N, we treat it like a number because that is the position of the methyl group, N-methyl. First name, pent. Last name, ane. Whenever you have your name ending in a vowel and this starting in a vowel, you drop that E. So it's pentan instead of pentane. Amide. And that's our final name. Any questions? I wish OChem was so easy at University of Toronto. Do you mean that you have more difficult problems that you get tested on? If that's the case, what you want to do is start with the easy practice, get really good at it, then more difficult, more difficult, more difficult. In fact, I have a stereochemistry practice worksheet that's not available on my website. Just comment stereo and I will reply with a link. Yes, even if you're watching the recording, and you'll be able to do a lot more practice on stereochemistry. Question, we don't write 4R, just R. Given that there's only one chiral center, we know that the R corresponds to the only chiral carbon on the molecule. If I had more than one chiral center, then I would have to specify. So let's say I had 2s4r, I would have to put 2s, 4r to show that I have, to show which stereo center corresponds with the R and the S in question. Okay, so that was a really good question. Let me know if that helped. And let's try another one. For this one, let's come up with a name, but also let's identify cis and trans for each of the pi bonds. So first thing I want you to tell me is how many carbons in the parent chain. Looking a little drunk here, but hopefully that still makes sense. All right, where do I begin? How many in my parent chain? Do I number from the right and the left? How do I approach this? Question, can you show how you know there's only one chiral center? I have a problem, a practice problem later where we're going to look at that, but ultimately you're trying to identify any stereo center in your molecule and go from there. So in this case, what looks like the parent chain is right here, but we have a junction. And coming out of this junction, I have short, medium, long. So I'm going to exclude the short and just continue counting my way down in the direction of the long. Then I want to number and get the total lowest set of numbers. So if I number from the top, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9. My pi bonds would be on 3, 4, I have a methyl on 7 and a pi bond on 8. If I reverse the numbering and I count here 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I have a pi bond on 1, a methyl on 3, a pi on 4, a pi on 6. Total lower set of numbers. So we're going to go with the red set. And for pi bonds, you only number the first carbon of the 2 sp2 carbons that you hit. So whichever one comes up first in your chain, that's the one we're going to count. All right, so cis or trans for each of the pi bonds. The way I look at a molecule like this, actually, let's put the name together and then we'll add the cis and the trans. So I'm just going to move that out of the way. We have 9 in the parent chain. That's a first name of non. We have 3 pi bonds. So that's the last name of ene, but there's 3 of them. So I have to put triene and I have to specify the number, exactly where they show up. So the pi bonds show up on 1, 4, and 6 triene. And I also have a methyl on 3. Oops, hit that once too many times. 3 methyl. There we go. All right, let's put the name together. We only have one substituent, that is 3 methyl. And then our first name is non, and our last name is triene. But in a situation like this, you pull the numbers out to the front, although I've seen professors do it both ways. So that would be 1, 4, oops, 1, 4, 6, non, triene. Oh my goodness, that looks messy. Another way that you can do this is 3 methyl, non, 1, 4, 6, triene, like that. And then we have to figure out cis and trans. So what do you think for each one? I'm going to, actually, let's go by the numbers. So let me know for pi bond on 1, 4, and 6. Do you think they're cis or trans? the way I like to rank them, or a quick way that I like to look at them is like this. If I have a pi bond, when I'm looking for cis or trans, if the two groups are next to each other, cis, like sisters, they're close together. If they're opposite from each other, trans, they transfer away to opposite ends. And an easy way to do that is to just draw an arrow coming from your sp2 carbon. That's a little bit small, so let me show that to you in bigger, because on your exam, you can do this in a pen or a pencil, and it'll be very clear what you're doing. Here we go. So you take the carbon holding the pi bond, and you just draw a line. They're coming to the same side. They're going to opposite sides. So let's try that on 6. Opposite sides. So we see that 6 is trans. We'll try that on 4 to 5. Cis, they're going to the same side. We'll try that on 1 to 2. I have this one, but where do I draw the line here? I don't, because this is terminal. And if it's terminal, it has 2 hydrogen atoms. This is not cis, and it's not trans. We only have 2 stereo centers for the pi bonds here, although technically that's also a chiral center because that would be a chiral carbon. I didn't draw that in a dash or a wedge, so you don't have to include it. I was focusing on the cis and trans. And that means we have 4 cis and 6 trans. Now I saw questions about E and Z. You can use the E and Z notation as well. You don't have to just use cis and trans. Typically like this, you'll use cis and trans, but if there's more going on in the molecule, you will see the E and Z notation. The way I think of them is very similar to what I have here, but with E and Z, you often see it when you have more things going on. So let's say I have a hydrogen and a bromine here, and I have a hydrogen and a methyl group here. You look at each carbon of the pi bond, and you draw a line to the higher priority substituent. In this case, it's a bromine. In this case, it's a methyl compared to hydrogen. And then the 2 notations that you can use are E or Z. And here's how I like to think of it. E stands for opposite. If the 2 substituents are on the opposite side, like in trans, that would be E. And Z stands for the same side. So when the 2 substituents are on the same side, then they are Z. So if they're together, they're Z. If they're opposite, then that's E. All right, so looking back here, because there's nothing else going on, they only have hydrogens as the other atoms here. The trans would equate to E for opposite, and the cis would equate to Z for the same side. LMAO. Whoops, I meant to do this one. So my professor, no, not my professor, my lab professor was foreign and had an accent. And that's how he spoke. They're on the same side. so that's how I got the mnemonic. He accidentally came up with it, but I don't think he noticed that he came up with it. I remember Z by pretending GRU is saying together in his, I don't know who GRU is, but whatever works, right? Let's try this one. As I'm drawing this out, let me know if you think this problem is easy, medium, or hard. Maybe let's not go that crazy. So we'll do that. All right, here we go. Easy, medium, or hard. And where do we even begin this? People use that mnemonic all across the country. So I don't know who came up with it, but I put it in a video over 10 years ago. So I do hear my tricks coming back to me. Not all of them I came up with, but some of them that I came up with. I love when people tell me, yeah, my professor taught me that. And then my professor also gave me a quiz with your name on it. I would cry if I saw that on my exam. Well, let's change it. Let's make this so easy. Let me see fire emojis in the comments if you want this to be so easy or so doable that you can totally get this right on your exam. Where do we even begin? Well, first, we want to find the longest carbon chain. And given that I don't have a million branches coming out of it, the longest carbon chain is exactly what I see here. So that's an easy part. The next thing I want to do is figure out if I'm going to number it from the right or the left. But in this case, I don't have to worry about the total lowest set of anything. All I have to do is identify, hey, carboxylic acid, highest priority. And here is a trick for you. The highest, whoops, where's my pen? The higher the oxidation number, meaning the bonds to oxygen, is going to be the higher priority. So if you look at your functional group priorities, and I have a cheat sheet for this on my website, you'll see that a carboxylic acid is higher priority than an aldehyde, which is higher priority than an alcohol, which is higher priority than a chlorine because of the number of bonds to oxygen, the oxidation number. And with a carboxylic acid being number 1, I just start numbering from here and I'm good to go. Now here is how this is going to be doable. Maybe not easy, but here's how we're going to make it doable. We're going to take it one step at a time and mark everything that we do so that we don't forget anything. So we have the parent chain. We're going to start with the first name. I see 7 carbons. That is hept. I see 1 pi bond. That means I get a last name of -ene, and it's on carbon 4. So that's 4-ene. For anyone taking the ACS, because I see a question in the comments, just go to layerforset.com/ACS. I have a whole guide on how to prepare for that. So we have hept 4-ene, and I want to mark that I got the pi bond. Now I'm just going to work my way across and mark each one. Carboxylic acid is my highest priority. That means the molecule is going to end in the name oic acid. Then we're going to take our substituents one at a time and make sure we don't forget stereochemistry. I have a methyl on carbon 2. That's 2-methyl. I have a cyclopentyl, because it's a ring, on carbon 4. Let's move this tip out of the way. I have the 4-cyclopentyl. I already got the pi bond. I have an alcohol on carbon 6. Because it's not the highest priority, it's demoted to a substituent as 6-hydroxy. And I have an aldehyde on carbon 7. Again, because it's not the highest priority, it's demoted. I have seen it's called formal and oxo. I learned it as oxo, but some professors teach it as formal. Both of them are perfectly okay. Oxo also works for ketones. If it's at the end of the molecule, it's an aldehyde. If it's in the middle of a molecule, then it's a ketone. Then we're going to put the whole name together in alphabetical order, starting with the substituents in alphabetical order. I have M for methyl. C is not what we use for cyclopentyl. It's the P. The cyclo doesn't count. H for hydroxy and O for oxo. So that is HIJKLM and OP. OP. So HMOP. So we'll start with H for 6-hydroxy, 2-methyl, I left out a dash there, MNO, 7-oxo, 4-cyclopentyl, and here we can pull the 4 to the front of the molecule, to the front of the parent name, so 4-heptene, We drop the E because of the O for oic acid. Heptene oic acid. Not bad. It's a lot, but do you see how I kind of went through it piece by piece by piece and everything just fell into place? Okay. Then we have to do stereochemistry. So let's do that really quick. We'll start with the 2. So we have a hydrogen going to the back. And hydrogen is always number 4. Methyl in the presence of hydrogen is always number 3. This direction of the chain hits a carboxylic acid. That is 1. This direction does not. It takes CH2s and CH2s. So that's a 2. I'm doing this fast, but go through the stereo worksheet so you can go through this concept more slowly and just get really good at stereochemistry. Again, put stereo in the comments and I'll link you to the worksheet. Cross out number 4. Trace an arc from 1 to 2 to 3. And that means I have 2R. This time, because I have more than one chiral center, I do have to specify that 2 is R because I don't yet know what 6 is, but let's find out. I have a hydrogen going to the back. So that is, what color am I going to use? 4. No, that's not clear enough. Now let's do this color. 4 in the back. Alcohol is an oxygen. That is priority number 1. This carbon hits a carbonyl to an oxygen. So we hit a carbon, double bond, oxygen, carbon. So that will be number 2. This will be number 3. We cross out number 4, trace an arc from 1 to 2 to 3. I get S, and I have to specify 6S. So 2R and 6S. Then I have the rest of the name, and I'm good to go. What do you think? Slightly easier than what we started with, or what you thought it was in the beginning? Question, why is it YL? Anytime I have a substituent, the YL tells me that it's sitting on something else. And so methyl is meth, 1 carbon as a substituent, YL. Cyclopentyl is a cyclopent, a 5-carbon ring as a YL, as a substituent. So that YL tells me that it's a substituent. Question. To clarify, we only assign stereochem when there are dashes and wedges. Well, we have to know if it's chiral, what kind of chirality we're dealing with. So for example, here, how are you going to assign this RNS if I haven't told you if it's coming out of the page or going into the page? It could be both, but because I didn't specify, you're not able to tell me. If I drew it with a dash or a wedge, then you would give me the correct answer based on what you figure out. And for the stereo worksheet right there. Okay. All right, so for even more practice on nomenclature, I actually have a very, very good quiz on my website. It's something I worked really hard on. So just put nomenclature in the comments and I'll link you to the quiz. That way you can continue practicing on nomenclature. As we move on to the next topic, let me know if you think this question is easy, medium, or hard. We want to complete the acid-base reaction and predict the direction of equilibrium. All right, so what happens in this acid-base reaction? And then if I show this as equilibrium, will the reaction favor the reactants or the products? The way to first figure out how to finish this practice problem, meaning how to finish the acid-base reaction, is to identify if you have a positive or negative charge. That is the easiest way, in my opinion. If I have something that can be deprotonated or is deprotonated, then the more negative will steal a hydrogen from the more positive. So in this case, anytime I see an Na, I recognize that it's a positive spectator. I get rid of it. And then it will grab a hydrogen from the other molecule. So to complete this reaction, let's grab parts of it because I don't feel like redrawing so many. We took the hydrogen from the first molecule and we added it to the second. And so that means I have a hydrogen here that I had initially. And now I have another hydrogen. This one here is left efficient with a negative charge, so I can give it the counter ion, the Na+. The Na+ just tells me that there's a minus next to it. Now that I have my completed reaction, is this going to favor the products or the reactants, the right or the left? And the way you figure this out, well, there's a couple of different ways to figure it out. I like to use the mnemonic CARIO, which I teach in my acid-base videos, where I'm going to compare charge, atom, resonance, induction, and orbital. Looking at this right here, I can identify both pairs, where this right here is an acid-base conjugate pair. The more positive of the two is the acid. The more negative of the two is the base. And because this product is the conjugate base, same thing for this set right here. The negative is the base. The more positive is the conjugate acid. Now, what am I saying more positive? This is neutral. Neutral is more positive than -1. And then if I can identify the base on one side and the base on the other side, I can find which one is more stable, or the acid. But typically, I like to compare the two charged molecules. And so what I'm looking at here is really a comparison of this one right here or this one right here. What is the difference between them? I have an N- or I have an O-. Which atom is more capable of holding a negative charge, meaning which one is more electronegative, wants that negative charge? Again, CARIO stands for charge. Which one is more positive or negative? Atom, which atom, electronegativity is what I'm looking at, is holding the charge. Resonance, can the charge be stabilized by sharing it between other atoms? Induction, the inductive effect is the nearby group stabilizing. And orbital hybridization is if I'm looking at an sp3, sp2, or sp with regards to that acidic proton. And in this case, if you look at the periodic table, I highly, highly recommend memorizing these 10 atoms as follows. H, C, N, O, F, go down your halogen, Cl, Bri, and here we have sulfur and phosphorus. The reason this is so helpful is you don't have to keep flipping back to your periodic table. You just recognize that electronegativity goes up to the left, charge goes down. That's not the left, that's the right. Up to the right, and size, not charge, goes down to the left. So in this case, if I'm comparing N to O, O is more electronegative. Therefore, it is more stable. It is more capable of holding the charge. And if the one with the charge that is more stable is on the product side, equilibrium will lie to the right. Question, what about pKa's? pKa's makes it very, very easy. Just look at your pKa value and determine which one is stronger or weaker based on the number. But for this topic, professors will intentionally not give you a table. So using CARIO, you will learn to rank them based on stability, because pKa's are typically not given at the organic chemistry level. If you're trying to figure out which side of a reaction is favored, the size with the largest, okay, so pKa value matters if you're looking at acids or bases, protonated, deprotonated. I'm challenging you to solve this based on stability, because if you're not given a pKa table, I want you to be able to solve it with just looking at it. The overall charges, neutral, negative, neutral, negative. So I was looking at the stability of the one that is less stable. Negative is less stable than neutral. So which side, right or left, has the more stable, unstable version, the more stable, unstable molecule? My professor told us to memorize pKa's, but never told us which. That is not very helpful. I would recommend memorizing some of the basics. No pun intended there. Water, alcohol, an acetylene, a phenol, carboxylic acid, ammonia, like the ones that you're going to see a lot. But then I recommend learning this. So if you don't have a pKa table or a value memorized, you can still rank any molecule. So let's take a look at another problem. Same situation where I give you two molecules and I want to figure out the product of this acid-base reaction and then determine which side is favored by equilibrium. So if I react a phenol with a sodium ethanoate, I missed it over there. First thing I want to do is complete the reaction. What happens when I react phenol and sodium ethanoate? The sodium is a positive charge spectator. This right here is negative. And so the negative is going to grab a hydrogen off the other potential acid. So that is my first step. I'll just copy this piece over. So now I get a deprotonated phenol, a phenoxide. It's going to have the counter ion because this is negative, this is positive. And then I now have a carboxylic acid with a hydrogen that I got from phenol, and then the rest of it. Okay, that should not be a right arrow just yet. The question is, which side is favored by equilibrium without using pKa values? I want you to reason through this logically. We'll use CARIO again and go through it slowly. Charge, well, the charge is the same on both sides. I have one negative and one neutral. So let's pair them up real quick. This right here is an acid, and this is my conjugate base. These pair up to give me a base and a conjugate acid. In each case, the base is negative and the acid is neutral. Not really helping us with charge. Atom. Which atom is holding the charge? Oxygen and oxygen. Not able to use atoms here, so let's move on to resonance. Which of the negative charges are stabilized by resonance? Well, actually, both of them are, but this is where it gets interesting because the resonance is different. For the phenoxide, the deprotonated phenol, how many resonance structures can I draw compared to the ethanoate, the deprotonated ethanoic acid or carboxylic acid? That's a negative, and that's a negative. This is where it gets interesting. And I'm seeing multiple questions on CARIO. So go to layerpsi.com/acid-base. You know what? Here's what I'm going to do. I'm just going to put these links into the description. And that is the acid base and the ACS chemical report as well. So I'll make sure it's linked below this video. For the first one, I have 1, 2, 3, 4. 4 resonance. For the second one, I have 1 and 2. 2 resonance. And I'm not going to draw them out for time, but I highly recommend that you practice it. So just draw them out for practice. If this one has 4 resonance and this one has 2 resonance, which of the two do you think is more stable and therefore better capable of holding that negative charge? The upper, the phenoxide, or the lower, ethoxide? If you're not sure, put IDKY. This is a trick question, and so I intentionally put it into today's review so you don't miss it on your exam. Yes, this one is 4 resonance and this one is only 2, but look at the periodic table again. Oxygen is way more electronegative than carbon and therefore way more capable of holding a negative charge. And so in each case, it's an oxygen holding that negative, but the question is, who is helping that oxygen? For the first one, we have an oxygen plus 3 carbon, and for the second one, we have an oxygen plus an oxygen. So here's the scenario I want you to imagine. My son is almost 3, and he likes to help. When he helps, he drops things. They're heavy. He gets lost on the way to where he's supposed to go, and half the time, I'm just cringing, hoping that he doesn't destroy whatever it is he's trying to help. In the case of this one right here, oxygen is big and strong. It's carrying something, but it needs help. Would this oxygen prefer 3 toddlers helping? And they're kind of sort of helping. Like when we bring in groceries, my toddler will bring in the light things, and he's so proud of himself. Or would you rather have a big, strong adult? So would I rather have my husband helping me carry in the groceries or my toddler and 2 of his friends? My toddler is 3. They all like to help. I'm going to go for the big, strong adult who I trust not to drop everything. And so even though it only has 2 resonance, it's 2 highly electronegative atoms. Therefore, this is more stabilized. Therefore, we favor equilibrium in the direction of the more stable negative. Equilibrium will go towards the, hold on. Did I just draw? Oh, wow, that's not a negative. I mistook that H for an N. We're going to go this way because this is more capable of holding that negative charge. Matthew, sorry about, no, sorry, not sorry. All right. So that, yeah, oh my goodness. I had high hopes for today. I had like a gazillion more problems, but let's say we keep going. Who wants to keep going with some more crazy problems? Newman projections, chair conformations, stereochemistry. See yeses and nos in the comments. Yes for keep going and no for now. Let's call it a day. As a reminder, for a copy of the session notes from today, so everything that I'm covering, you'll be able to see everything I drew, all of the practice problems, be able to redo them again, as well as the part 2, because this is only part 1 exam review. Part 2 is going to cover reactions. Go to leahforstat.com/orgolive. Sign up there. I will send you an email. If you sign up after the fact, you'll get an automated email that will have the links already in it. So leahforstat.com/orgolive for a copy of tonight's session notes and so much more. No, so reactions will be in part 2. But what I will show you today is this one right here. For this problem, we want to find the relationship between the 2 molecules as follows. For the first one, I have an ethyl, a bromine, and an OH. For the second one, I also have an ethyl, a bromine, and an OH. And then in the back, I just have hydrogens. If you see this on your exam, what is your approach? What is your reaction? Crying, which I saw before, or panic. Crying is allowed in practice. Panic, no. We can't afford panic on the exam because if you panic, your mind goes blank and you're done. Take a deep breath and ask yourself, what is the question? What do I do? Option 1 is you can go through each one and find R and S. And you could either do it on the Newman projection or you can turn it into a 3D molecule and find R and S that way. I'm guessing you don't want to do that. I'm guessing you want a faster way. So let me see a smiley face in the comments, smiley face emojis for a much, 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 much faster way. Unless you're asked for R and S, then you're going to have to do it the long way. But here's the thing. If you recognize that you have the molecule pretty much set up the same way. I have a Newman projection. The rear carbon has 3 hydrogens. Well, that's just a methyl group. The forward carbon has the same substituents. So let's ask this question. If I have to find the relationship between these 2 molecules, the relationship, once I've confirmed that they have all the same groups, but they could either be the same or enantiomers. If the molecule is the same, it's exactly the same. It doesn't matter if it's R and S. If the molecule is enantiomers, it'll be opposite or mirror image. Doesn't matter which one is R and S. So let's find a way to just go circles and circles, and if they're the same, they're the same. So let's just pick a random order where we're going to go from OH to ethyl to bromine, clockwise. Not necessarily R or S, just OH, ethyl, bromine, clockwise. OH, ethyl, bromine, counterclockwise. If the molecules are set up exactly the same way, but one is clockwise, one is counterclockwise, is that not exactly the definition of an enantiomer? So why would I waste my time doing anything else when I can tell you right here and now that these two are enantiomers? One goes clockwise, one goes counterclockwise. What do you think? Easier, faster, more doable? If you did have to find RNS, because sometimes your professor's just not that easy. Let me show you a shortcut for that as well. But first, can you say that again? Yes. If molecules that are the same are exactly the same, and molecules that are enantiomers are opposites, they're mirror images. One goes this way, one goes that way. If I can find a pattern and follow it around the Newman projection, if I follow it around the same way, they're the same. If one goes one way and one goes the other way, that by definition is the enantiomer. So I randomly choose 3 substituents and note the order. So basically I'm turning the wheel one way or the other. Let's randomly go with bromine, oxygen, ethyl, bromine, oxygen, ethyl. Notice that one goes clockwise, the other goes counterclockwise. The same exact substituents, one goes one way, one goes the other way, that makes them enantiomers. If I do need to figure out RNS, I have seen turn them into a 3D, turn them into a Fisher, turn them into a unicorn. How about we don't do any of that? Here's what I want you to do. Just number your priorities. We see that the back has an H and H and an H. That means in the back I have a CH3. So I'm just going to put CH3 on dashes, because isn't this Newman projection really just this thing coming forward, this thing coming forward, this thing coming forward, and that going backwards? So I'm just going to look at the Newman projection that way and start prioritizing. Looking at the atoms, same periodic table that I told you to memorize. Look at that. We have a carbon, an oxygen, and a bromine. This is why it's worth memorizing. Bromine is 1, oxygen 2, carbon is 3. So I have bromine is priority number 1. Oxygen is priority number 2. I have an ethyl and a methyl, but remember the shortcut. Methyl in the presence of hydrogen is 3. In the absence of hydrogen is 4. And that makes this one 3. And now we do the same approach that I would with a regular chiral molecule. Make sure number 4 is in the back and cross it out. 1 to 2 to 3, this is R. And because I already established that they're enantiomers, this is S. Was that faster than anything else you could have done? 3-dimensional redraw, Fisher projection, unicorn projection. I'm totally make up the unicorn because I don't like doing a lot of extra hard work. So this is what I find to be a faster way. If you did not have number 4 in the back, just use the swap method and just keep the numbers on the dashes right there. Same shortcut, same priority, the same trick applies. And in the stereochemistry, where is it? I'm going to link again. In the stereochemistry worksheet, the one that's not available on my website, I have Newman projection problems like this and Fisher projections and more. It's free. Just comment stereo and I will send you a link. Even if you're watching the recording, I want to make sure you get access to the practice. Question, why is Br higher priority than OH? We're looking at the atomic number. So the higher the atomic number, the higher the priority. And the 10 atoms that I have you memorize, I'll just draw them out here again. You have H, C, N, O, F, halogen, Cl, Br, I, sulfur, phosphorus. So your priorities are iodine, bromine, chlorine. These are arrows. These are drunk arrows. Let's try them again. Iodine, bromine, chlorine, sulfur, phosphorus, fluorine, oxygen, nitrogen, carbon, hydrogen. Hydrogen is always number 4. Methyl in the presence of hydrogen is number 3 because it's the lowest that you can get. In the absence of hydrogen, it's the lowest that you can get. That is why these shortcuts work. Brody, I have an entire video series that covers the swap method and more. And when you sign up on, the link for the stereo worksheet will also, I'm pretty sure, link you to the series. And so you'll be able to review it there as well. How would you do it if it's not a CH3, but 3 different groups? Well, if you had 3 different groups and you potentially have a chiral center in the back, then you treat it as 2 separate problems. The problem in the front, the problem in the back, but same thing. And I think I have one problem like that on the stereo worksheet as well. If I don't, email me and I'll send you. I know I did a problem like that somewhere. All right, how about a torture of a problem for our next one? Is this worthy of a torturous problem in Fisher projections? How about we make it so that fissures do not end you? Are you ready to see that fissures are quite doable? Let's take a look. First thing is I want to see what the heck we're dealing with. So we have a 5-carbon chain with an alcohol on carbon 2 for my 2-ol and a bromine on carbon 3. How many stereoisomers do I have? I have a chiral center here and a chiral center here. To find the number of stereoisomers, I will use 2 to the n is the max number. In this case, it's 2 squared. So I have 4 possible stereoisomers. So part 1, 4. RNS for each and the relationships. I'm going to start with the relationships first. Let me know if this is something that you find hard. And if yes, let me see a thumbs up in the comments if you want to see a way faster way to draw them and find the relationships. All right, so what we're going to do is start with 1. I have a Fisher projection. And what I like to do is, this is my first chiral center, my second chiral center for carbon 1, 2, 3, 4, and 5. And I'm going to randomly put my OH on the right and my bromine on the right. That makes this a hydrogen, this a hydrogen. Up top, I have a methyl, and down I have an ethyl. I drew this achiral so I can set them up however I want. Now I'm going to turn off my brain, because who wants to have their brain on the whole time? And draw all the Fisher projections that I am going to use today. These are so small. Let's draw them bigger. So the first one, we're going to do a straight enantiomer, exact opposite. So OH, Br, H, H, and that's a CH3, and that's an ethyl. Let's keep the carbon chain like this so it doesn't distract. Not sure what I was trying to do there. I was trying to do that. Okay, so there we go. That's a much better way to turn off the brain. So we'll do this. 1 and 2. So I have all my skeletons. And for the first one, I did a mirror image. Going down, I am going to keep one of the chiral centers, flip the other one, and then do the exact mirror image. So OH opposite, the H, and then H on the inside, bromine on the outside. Now that I see all 4 of them, to find the relationships, I would find RNS for each one. And then I would compare if I have R and R, S and S, S and R, RNS. That's one way to do it. Let me see hearts in the comments if you want to see a method that is so much faster. You're going to wonder why you ever did it the long way. Not the wrong way. That was a slip. The long way. All right. For the first one, I told you to flip it, right? All I did was draw the exact opposite. So of course they are going to be enantiomers to each other. For this one right here, I told you to flip it. So of course they are going to be enantiomers to each other. These are the only pairs of enantiomers. Now to go from the upper to the lower on the left, I said keep one the same and flip the other one. If I keep one the same and flip the other one, that by definition is a diastereomer. And if these are the enantiomers of these two, they would also be diastereomers. And if this one is the diastereomer of this one, it will also be the diastereomer of the enantiomer. So that makes these diastereomers. And these are the exact opposites, so they are also diastereomers. And I still don't know which one is R, which one is S. And I don't have to. Much faster way to find the relationships, right? I have my enantiomers, and everything else is going to be diastereomers to each other. Now that I know the relationships, I can't forget that I'm still having to find R and S. Now, some professors will not ask you for R and S, so you are done. You're good to go. But if you do have to find R and S, now we're going to have to do it the long way. So I'm going to make this one slightly bigger so we can see it and work on the chirality here. We're going to take one carbon at a time. First, where did the comments go? This is so much easier. Well, professors teach you the long way, but you had mentioned something earlier that fissures were not your thing. Is it starting to look like maybe fissures are doable? Let's make it even easier. We'll start with the chiral center for the upper one. Alcohol is 1. Hydrogen is always 4. Methyl in the presence of hydrogen is always 3. That makes the lower carbon 2. Cancel out number 4. Trace an arc from 1 to 2 to 3. But because hydrogen is on a wedge, we have to reverse it. This one is S. Let's do the same thing for the lower one. I have bromine is 1. Hydrogen is always 4. I have ethyl, which is just carbon to carbon, but this one is carbon to oxygen, so the upper is going to be higher priority. That's 2. Not where I meant to put the 2. 2 and 3. We will trace an arc, cross out number 4, arc from 1 to 2 to 3, but because hydrogen is forward, I reverse it. This is R. I know I did this really fast, so just try to see if you followed what I did. And if not, make sure you take the time to practice. But the reason I did it fast is because we need to find R and S for every single chiral center on this molecule. Or let me see, clapping hands emojis. If you want to see how I'm going to find R and S without redoing this another 6 times. So clapping hand emojis, go find those things. I'll take a sip of water and we are going to destroy this thing. Or party emojis, that works too. All right, they're coming in. Ready? We're going to apply some very simple but obvious logic. If this chiral center here is S and this one is R, but we established that this molecule is the enantiomer, should it not be the exact opposite where S will give me R and R will give me S? And if we establish that when the OH is on the right, the molecule, that chiral center is S, should this not also be S? And if bromine on the left is S, should this not also, with a bromine on the left, be S? Or we can say bromine on the right is R, then the opposite is S. Well, that would be S and S. And if this one is the enantiomer of this one, and we have S and S, should this not be R and R? Look at that. I found all the chiral centers, all the R's and S's by only finding one Fisher projections, R's and S's. Do you think this is faster, more doable, itty bitty more logical? Or as my kiddo says, EBBB. EBBB more logical. Question, how did you know the hydrogen was on a wedge? When you learn the Fisher projection slowly, you're going to go through the structure and see that it's coming forward with a bow tie and all of that I teach in my Fisher projection videos. But at this point, you have a final around the corner. We're just going to take the rule that if it's this way, then it is coming out at you and you have to flip it. So if hydrogen is this way, it's coming. Hold on. Why am I flipping it? Oh, yeah, because hydrogen should be in the back. So hydrogen needs to be here or here, but not to the right and left. Can you show how the second one is R again? Yes, so let's take the second one. I assume you mean the bottom one. So let's take this one, which is the same version, but not as marked up. So it's not as messy. And we're just going to solve this one. Let's make it bigger. Here we go. Priorities are as follows. Bromine is number 1. Hydrogen is always number 4. I'm dealing with this carbon, and ethyl is carbon to carbon. Up here, I have carbon to oxygen. Carbon to oxygen is higher priority, putting this at 2 and this at 3. I identify and cross out number 4, trace an arc from 1 to 2 to 3, which would be S, but if I have my number 4 in the horizontal, I have to reverse it, and that is how I get R for the bottom. So this was only half of the pre-finals exam review, covering the basics. Next step is reactions, which is exactly what part 2 is all about, and the link is in the description. We will be covering alkene, alkyne, radicals, SN1, SN2, E1, E2, chain elongation, and some synthesis and retrosynthesis. Go to layitforsci.com/orgolive, where you'll get a copy of tonight's session notes, tomorrow's session notes, and lots of bonus practice material. layitforsci.com/orgolive. I'll see you on part 2.